Interesting these ideas are. Some of these ideas are, one especially is very strange, very surprising, difficult to come to grips with, but useful. That's Gromov's result, which Gromov was here at Stony Brook for a while. He's living now in Paris. He was born in Russia. He's a great mathematician, for those of you who didn't know. He's done many, many very deep, very important things in mathematics. This little result that I'm going to be using this afternoon is not, he's not famous for that. It's just a little tiny half page in the middle, on page 149 of the book that he published in 1986. But I'm eager to share it with you. So this is joint work with other people at Raytheon. First result is a result that Alan was mentioning to me. Alan worked with these people at Lockheed Martin. I'm from Raytheon company. Lockheed Martin is a different big company, and we often compete. Don't always compete, but often compete. So these are competitors. These people are using the theory, part of the theory that I'll be talking about this afternoon, and works pretty good, as I'll show you. It's a plot of the error in the prediction of the future position of satellites. These are satellites very far away, geosynchronous altitude, very, very high altitude. And what's on the horizontal axis is the number of particles. What I'm talking about is particle filters, and I'll tell you what particle filters are shortly. But as you can imagine, the more particles, the better, whatever a particle is. Particles are points in d-dimensional space that represent a probability density of the state of some dynamical system. And in this case, the dynamical system is the orbit of the satellite. So they're estimating the orbit of the satellite. And they're predicting the future position of the satellite many, many, many hours into the future. So as you can see, the boring old extended Kalman filter has very big errors. But if you use a particle filter, say a standard particle filter with so-called bootstrap with resampling, you get more than an order of magnitude improvement in performance. That is, more than an order of magnitude reduction in the errors. But it's not as good as the new theory that I'm talking about this afternoon, the particle flow theory in blue. Now, one thing that I like about this comparison, besides the obvious goodness of my theory, is that I didn't do that. This was done by other people at Lockheed Martin on the other side of the continent in California. And I didn't help them. I didn't give them any code. I think that Nima sent me an email once and told me he was having trouble getting it to work. And I said, oh, there must be a bug. So armed with that extremely good advice, he went back and found the bug and fixed it and got good work. A third reason I like this is because it's not MATLAB. It's not simulation. This is real data with a real telescope. It's a very beautiful, expensive, big, well, pretty big telescope. The optics is about 1 meter in diameter. It's right in the middle there. It's on a sort of rails. There's a truck in the background at the very top middle of the chart, just to give you some reference. And it's a big modern telescope whose accuracy is improved, in a sense, by over 2 orders of magnitude if you use this interesting mathematical theory. So the filtering problem that I'm solving is much, much more general than just predicting satellite orbits. You could use it for all sorts of other things, like predicting the weather or predicting the stock market. Rumor has it that some people in this neighborhood actually do such things with Ito calculus. Ito calculus to make more money at the stock market. So, and it's pretty general. It's not as general as possible, but the dynamical system is described by a state vector x. X is d-dimensional. So for a satellite, the simplest model would be a 6-dimensional state vector, 3 positions and 3 velocities. But you can have much, much higher dimensions, as I'll show you later. And the theory I'm talking about applies to either discrete time or continuous time, evolution of the dynamics of the physical model. Doesn't matter. The same theory applies equally well to discrete and continuous time dynamical system. But the measurements are in discrete time. In fact, which is the practical problem of interest in essentially all real-world applications. And so we solved this problem. So this is sort of a textbook standard nonlinear filtering problem. By the way, you can also apply the same, essentially the same theory to much more general problems with jumps, problems with time delays, problems with integration, problems that are described by partial differential equations like Navier-Stokes equation, like the weather. So how do we do this? So particle filters are very popular. Invented sort of by a famous paper, 1994. Within 5 or 10 years, everybody was programming up particle filters, getting better results for certain problems than Kalman filters. But a big issue with the old particle filters is that they suffer from what is called the curse of dimensionality. And at first, very interestingly, the researchers who were developing these early particle filters would publish papers and give talks saying, our particle filters beat the curse of dimensionality, meaning that as the dimension of the state vector grows, the computational complexity to get optimal performance or good performance doesn't grow exponentially. I can name names, but I won't. So when I heard that, I almost fell out of my chair. I thought, no, that's definitely not going to be happening anytime soon with this kind of a particle filter. So we tried the particle filters for various dimensional problems. So that's the message of this chart. A one-dimensional state vector in black, you get optimal performance. By the way, unity is optimal. Unity is 10 to the 0th. That's optimal performance. You get optimal performance with about 100 particles. So you get nearly optimal performance with about 10 particles. That's intuitively reasonable. As you increase the dimension of X, the problem gets more difficult, as you would all immediately, intuitively know. And furthermore, of course, as you use more particles, the accuracy of the particle filter gets better. So those are the two primary observations about that picture. But just focus on the 10-dimensional example, the worst plot, the one in pink, or whatever that color is up there. So I guess that's pink. So we use 1 million particles, 10 to the 6 particles. And what's the answer, though? What's the accuracy we get? We get an accuracy of 10 to the 10th error relative to optimal. So that's pretty bad. Now, I haven't told you what the problem is. What is the actual application here? Is it perhaps some problem that I cooked up to torture particle filter researchers? Is it a problem that's especially difficult, which would give rise to that bad performance? No, this actually is the easiest problem. This is linear Gaussian problem, estimation problem. It's the problem which the Kalman filter solves exactly, in the sense that it gets optimal performance with very low computational complexity, d-cubed computational complexity. So, so I'm not torturing particle filter researchers with the example that I picked. Furthermore, after we published that in 2003, after about 5 or 6 years after we published that, Peter Bickel at Berkeley, University of California at Berkeley, proved mathematically, correctly, I believe, that this class of particle filters with resampling and a bootstrap proposal density must suffer from the curse of dimensionality. So it's not just proof by MATLAB. There's a mathematical proof by Peter Bickel. And then a few years later, Francois Leglande came up with a even much simpler, easy to understand proof It's a fact. Believe me, lots of other people have replicated these results. And the reason I'm showing it to you now is not to gloat, not to be so proud about this simple MATLAB exercise that we went through, but rather to show you what the problem is that we're going to be addressing. And the first step is to understand why is this happening, because it was actually a surprise to the early particle filter, to a lot of the community. There was some theoretical reasons for thinking that, well, maybe the particle filters would beat the curse dimensionality, but no. So now we will...
I'm terribly sorry. I'm from applied mathematics.
Good.
So I don't live in filters.
Good.
But do something with incomplete information.
Yeah.
Would you please show the previous slide and again repeat what is particle filter and what is the difference between particle filter and complete filter?
Well, it'll be the next.
Oh, I'm sorry.
It'll be the next couple. Okay. Great, perfect question.
Okay. Okay.
Yes, but don't apologize for being in applied mathematics. And furthermore, I love questions. I mean, one of the reasons I drove down here is because I like giving talks like this to audiences of people like you who ask good questions. So I would strongly encourage any question, simple question, complicated question, tough questions, because I love it. And furthermore, new ideas often come from such questions, not immediately. Not promising any new ideas this afternoon from such questions, but maybe when I'm driving back home to Boston, I'll think, that question was very good, and so we can make some hay with this. So any nonlinear filter consists of these two pieces. There's a prediction of the conditional probability density of X, and that's in the yellow box. It's a prediction over time. It's a prediction between one discrete time measurement and the next discrete time measurement. So that's the yellow box. And if it was a continuous time problem, to solve that problem exactly, you would need to solve the Fokker-Planck equation, some partial differential equation that describes the time evolution of the probability density. And the other box is in green. That's the box which updates the conditional probability density when you get a discrete time measurement. Every time you get another discrete time measurement, you use Bayes' rule, turn the crank with Bayes' rule, and you compute the new conditional probability density, conditioned on a bigger set of measurements. So the green box is incredibly simple. It's just a multiplication of two functions at a given point x. And I haven't bothered to normalize. That would be something else. But it's actually not necessary to normalize the probability density for the actual algorithm. But you can see that that's a very simple mathematical operation. It's like one instruction in MATLAB. So if you were to ask the question, where is the difficulty? Where is the curse of dimensionality that's causing the trouble on the previous chart? Any normal person would think, oh, it must be the yellow box, because this is solving a partial differential equation, big complicated computation. I won't even show you what the partial differential equation is, whereas the green box is so simple. How could there be any trouble?
Am I right? I'm sorry for interruption. Am I right that if we go to discrete time?
This is discrete time.
Yeah, then Fokker-Planck equation essentially is relevant to Bayesian formula, yeah?
You can think of it that way, and you'll see. So any normal person would think the trouble can't possibly be in the green box. It's too simple. Computers are fast and accurate at multiplying. Trouble must be in the yellow box. So that's what I thought for 40 years. That's what I was taught at a very expensive school, which will remain nameless. It's wrong. The trouble is in the green box. How is that possible? How is it possible that the curse of dimensionality could be caused by mathematical operations that is so simple as a single multiplication. We'll see. So this chart serves several purposes. It's a cartoon that serves the purpose of explaining what the problem is, what's the root cause of the problem. It also serves the purpose of explaining what a particle filter is. So we represent probability densities using particles, which are nothing more than points in d-dimensional space. And at each point, we know the numerical value of the conditional probability density. So all we're doing is representing that prior density, the blue curve, with numerical values. And we use 10 particles here. And those 10 particles are distributed approximately according to that density. So there's more particles where the probability mass is bigger. And you approximate that conditional probability density very, very accurately with those 10 particles. They're in the right place to do that approximation. And it's a very smooth, easy prior probability density, like a Gaussian density or any smooth density. And now we come along with a measurement. And so what a measurement is requires us to multiply the likelihood, that is the red curve, times the blue curve, the prior. So let's do it. Let's do it first at the particle on the extreme left. What's the answer that you get? The answer is essentially 0, because that particle, that point in x, is so far out in the tails of the likelihood. So you get a number, but it's essentially worthless. And do it at the second particle from the left. Same thing. You get essentially 0. Third particle, same thing, it's 0. Fourth particle, same thing. Same story to the right. The only two particles where you get a significant non-zero value of the product of the red and the blue curves are these two particles right there. And if I told you the exact product of the red and the blue curves at those two particles, this would be completely useless, because that defines a straight line, whereas the correct answer is some kind of bell-shaped curve. So here's what was going on. Those 10 particles are great particles. They're in the right place to approximate the blue curve. However, when I attempt to approximate the product of the red and the blue curves with those same 10 particles, it's a complete disaster. And this is called particle degeneracy. Particle degeneracy, because the set of particles to start with was great to represent the prior, but then when I used that same set of particles to represent the product of the prior and the likelihood, they've degenerated in this new application to be a complete disaster, total waste of time. That's the problem. What I have just told you is the problem with standard particle filters. I haven't shown you any formulas, haven't proven any theorems, but that's the problem. And in higher dimension, well, how would you fix this problem? So a freshman at Stony Brook would say, oh, just use more particles. So you use 100 particles instead of just 10 particles. Great, that solves the problem. Then I would have 10 particles in this region here. I would form a very accurate estimate of the product of the red and the blue curves. Problem is solved, except at a cost of an order of magnitude increase in the number of particles that you have to use. I need 100 particles, not just 10. If this was a high-dimensional problem, that factor of 10 occurs in every dimension. 2 dimensions, you would need 2 orders of magnitude more particles. 3 dimensions, you need 3 orders of magnitude more particles. 10 dimensions, you need 10 orders of magnitude more particles. That's exactly what happened in our very simple Monte Carlo simulation. So you can explain that simple Monte Carlo simulation, the effect of it, using this simple cartoon with no formulas, no theorems. Here's another important fact. See, the likelihood is the probability density of the measurement given the state. And the width of it represents the uncertainty in that measurement. So now let's make a more accurate measurement corresponding to a thinner likelihood. Now the problem is even worse. Here I've done something which I thought would be a good thing, which any normal person would think would be a good thing. make more accurate measurements, better measurements, more expensive measurements, makes the problem worse. Now, none of the particles are useful. So how do we solve this problem? Well, almost all research in particle filters in the last 20 or 25 years is focused on attempting to solve this problem, but I'll show you one way.
Fred, may I just make
Peter.
one comment because
Of course.
my own calculations
Yeah.
on this problem. So if you can imagine that you'd like to sample from the unit interval from 0 to 1, and you want to get a particle in the interval that is of size 0.2, so 20% chance to get one particle there. So now imagine that you have this hypercube with size 1. And then in each direction, you want to get a particle in that interval of 0.2. If the dimension of that cube is 59, and if you sample 1 million particles a second, the time you have to wait to get a particle in that very small cube is longer than the duration of the universe.
Well, we can fix that problem by making the age of the universe. And that'll happen naturally for free, won't it? So
59 is the dimension.
59. Okay. Thanks. Thanks, Peter. So the way we're going to fix this problem, the way that we like to fix this problem, the way that we have found is very effective, very computationally effective and accurate, is to move the particles slowly and gradually to take the same 10 particles, don't change them, don't resample them, no new particles, don't throw out any particles. Take those 10 particles, move them somehow or other so that they're focused in the region of largest a posteriori probability density. How do you do that? Well, at first thought, not so easy, because I cannot tell you what is the product of the red and the blue curves. If you were an algorithm designer or a mathematician or applied mathematician and you said, well, Fred, what's the problem? Please just tell me the problem and I'll solve it. I can't. I can't give you the target density that I want. That was the problem to begin with. I cannot represent the target density because it's the product of the red and the blue curves and I don't have enough particles, or they're not in the right place to give you an answer. So we need something else. This is a chicken and egg problem. To solve the problem, I need to somehow do something else. Doesn't mean it's not soluble, however. There are other chicken and egg problems that have been solved. So what we do is we apply the following theorem. The theorem is if you cannot solve the problem all at once, then try and solve it a little bit at a time. And what we do is start with a high school definition of a flow of a probability density. So the log of P is now the log of G plus lambda log of H minus the log of K. K is the normalization. It's the integral of G times H with respect to X. It would make the volume under the curve P unity. This is just a logarithmic version of Bayes' rule. If lambda is 0, then P is equal to G. It turns out the normalization is unity in that case. But when lambda is unity, when lambda evolves to unity, then P is equal to G times H, which is what we want. We want to form the product of G times H. So we're going to do it a little at a time by allowing lambda to evolve from 0 to unity. 0 to unity. Good. So that's good. That's at least telling the mathematics what we want. We want to compute P a little bit gradually as lambda continuously evolves from 0 to 1, going left to right. But that's not enough, because if we succeeded in doing that, we would still have to sample from probability densities. And sampling from arbitrary high-dimensional densities, even if they're smooth, is big trouble, believe me. So a way around this is to ask for a law of motion to move the particles directly without sampling from the density. And that's the stochastic differential equation down there. dx is equal to f by times d lambda plus dw. dw is some increment of Brownian motion. So that's the most general stochastic process with continuous sample paths. Pretty general, not the most general. It doesn't allow jumps. It doesn't allow time delays. And that's the law of motion that we're going to try and discover. So the way we'll discover it is just a direct calculation with something like the chain rule. So it's pretty elementary mathematics. And I'll just review at this point. So what I started with was complaining about the Cursor dimensionality for standard particle filters. And then I said, well, what causes that is the fact that the particles are in the wrong place to represent the product of the prior and the likelihood. We have to somehow move those particles to a new place. And the particular method we'll use to do that motion is to derive a law of motion, which I call a flow of particles. So we want to compute the function f. And it turns out the equation that you have to solve to do that is this partial differential equation. The divergence of p times f is equal to p times that other stuff. And now the question is, can you do that? Or in what cases can you do it? What special cases can you do it? And what's the computational complexity of doing it? So I am absolutely not suggesting at all to solve that partial differential equation numerically. I believe that would be counterproductive. Numerical solution, unless I'm very, very mistaken, would be a waste of time, would be more effort than we're trying to save. But what we're going to discover is we can solve that partial differential equation analytically as a formula, an exact formula, as I'll show you. In fact, I'll show you 4 examples of that quickly. But first to say that if you had to solve a partial differential equation, that is about the nicest, easiest, simplest partial differential equation because it's linear. It's linear in the unknown f. It's first order linear partial differential equation. You might be able to solve it with the method of characteristics or something like that. And in some certain cases, well, if you redefine the variable as p times f, then it's a constant coefficient. So constant coefficient, linear first order partial differential equation, essentially the easiest possible partial differential equation. So there's hope. But first, a little intuition about what the particle flow actually does. Here's a simple 2-dimensional example. These little blue dots are the particles. There's about 1,000 particles. Here's the initial probability density represented by particles. It's a uniform density in angle and a uniform density in angle rate. And now I make a single measurement of the sign, the SIN, of theta, and attempt to estimate theta and theta dot, theta and its time derivative. So we'll show the effect of making a single discrete time measurement of the sine of theta, and we'll do numerical integration with Euler, 0.1 steps in delta lambda, simplest imaginable numerical, and that's the answer. So this uniform distribution evolved as a result of following the law of motion to be a bimodal distribution, which is the right answer. If you measure the sine of theta, that doesn't tell you theta. Theta could take on any of, even with zero noise, theta could have 2 different values. Show that again, because it's so much fun. So make a single discrete time measurement of the sine of theta, and you get the right answer with this law of motion directly moving the particles. I never sampled particles from a density. I never threw out particles. I never edited particles. I never identified bad particles or good particles. You just do this law of motion. It's physics. Physics is about moving particles. Physics is about laws of motion, so it's more like physics. So,
I'm sorry, can you explain that flow again?
I will. Oh, well, I'll show you some examples. When you say explain the flow,
Not that. No, not that.
You mean explain
No,
this?
not the
This?
previous slide.
Yes, I'll show you with examples.
No, I kind of.
So just be patient. I promise. If I don't answer the question, remind me and
I'm just afraid that I could not follow without understanding further, so I'm gonna.
that'll jump a slide. So there's no unique solution to this problem. After all, I start with a random initial set of particles corresponding to an initial probability density, and I want to compute another random set of particles corresponding to another given probability density. This is called the transport problem. There's no unique solution to that problem. There's an infinite number of different solutions. And likewise, the different methods that one can use to solve this partial differential equation are quite diverse, because it's linear, constant coefficient, and first order partial differential equation. Essentially any method for solving partial differential equations that you can name, almost, can be brought to bear, such as take a Fourier transform. It's a linear, constant coefficient partial differential equation. God intended us to solve linear, constant coefficient partial differential equations with the Fourier transform. In this case, it turns out it's not exactly a good idea to do that, as I'll explain later. Another method that you might use is ask your friends in fluid dynamics, hey, have you ever solved an equation like this before? And if so, how did you do it? And make it simple and easy. And the answer is, of course, 200 years ago or more, or Euler 250 years ago or more, decided to solve a certain fluid dynamics equation by making the assumption that the fluid is incompressible, meaning the density of the fluid is constant along the flow of the particles. That kills one of the terms in the partial differential equation. All sorts of other tricks that you can use, including Gromov's, that I'll be explaining shortly, but there's a plethora of methods to solve this. So I'll attempt to answer your question. I'll see whether this works. I'll show you three concrete examples. This one is the easiest. This one is the homework problem that everyone should do if you were interested in this topic. It's what happens if the problem is Gaussian and linear. Linear measurements, linear dynamics, Gaussian noise. So it's the same as the Kalman filter problem, but it's solved using a particle filter, exactly. So there's the partial differential equation at the second line. We wish to compute a function f, which is the solution of that partial differential equation, called the flow, and that is the exact solution. F is exactly equal to ax plus b, where A is a matrix that's displayed there using quantities that are familiar from Kalman filters. The measurement noise covariance is R. The prior covariance matrix is P. Lambda is that independent variable that I defined. H is the measurement sensitivity matrix. And B is similar, but now B depends on the discrete time measurement Z. So 2 lines of MATLAB, numerical integration with just Euler integration with step size of 0.1 works. Does that help?
No, I think what I'm confused is you said there's a problem of the first of dimensionality.
Yes.
So the observation update, you multiply the likelihood with the prior.
Yes.
Which correspond to lambda equal 1.
Yes.
And you start with lambda equals 0.
Yes.
And you said going one step is very difficult. So
Yes.
to get to degeneration of the particles.
Right.
So you try to attempt to do it at multiple steps.
Right.
For lambda from 0 to 1.
Right.
I didn't quite understand how it is done and how it actually resolves the problem of the curse of dimensionalities of the degeneration.
The way that it fixes, well, actually I am not asserting that I've beaten the curse of dimensionality, it turns out. All I'm asserting is that for certain problems that we've investigated so far, it speeds up the calculation by many orders of magnitude. right? Maybe 6 orders of magnitude, 10 orders of magnitude.
I don't understand like how you go from lambda from 0 to 1. That is something I'm not quite.
This little movie, I'm numerically integrating this law of motion. The law of motion, dx is equal to f of x, etc., is a law of motion, as in physics, like F equals ma.
What is F again?
F. So that, an example, I think, is the best way to understand what is F. F is that function in this special case. In the special case of linear measurements, linear dynamics, and Gaussian noise.
So F
It turns
F
out
is the motion model of the particles.
it's a calculation that I do to move the particles corresponding to Bayes' rule. This is not motion in time. What I'm talking about is not motion in time. It's motion as lambda evolves at the discrete time instant of a particular measurement.
So is that right that instead of having more particles, you're going to have more time in between? Is that
Yeah.
trade-off between?
Yes. That's right. That's a good way to say it. I keep the number of particles fixed.
But you increase the sampling time, so or it's somewhat you trade off between the spatial resolution with kind of temporal resolution. Is that what you
No, because there's no time here. Time is not evolving in this process that I'm focusing on. Time is fixed. Time is at a fixed, discrete measurement time. There's no time.
okay, maybe you should.
You'll-
I still.
Second example. Here is what would happen if you assume that the flow of particles was just like the flow of air or water, and it's incompressible. So air and water at normal laboratory conditions is in fact incompressible to very high accuracy, at least subsonic. You get a simple formula again. The flow is in the direction of the gradient of the log of p, with a speed that's proportional to the log of h, and normalized by the gradient of the log of p. So that's another explicit closed form exact formula for the law of motion, F, to move the particles so that they move from lambda equals 0 to lambda equal 1 to a position that corresponds to the product of the likelihood in the prior density. It does what I want. That's derived in order to do that. Third example is a geodesic flow, meaning it's the shortest path in some probability space. Here, you got another law of, it's a completely different law of motion. This flow in particular, the law of motion doesn't depend on the normalization. Even if you multiplied p times any positive function or number, k, called k, that formula would kill that k. You're taking the gradient of the log or the Hessian of the log of that product. So k doesn't matter. K is completely irrelevant and would be killed if you put it in. So the interesting thing is the partial differential equation that we're solving certainly depends on k, capital K. However, the answer to the partial differential equation doesn't depend on k. In fact, it's strongly invariant to k. The previous example, same story. The original partial differential equation depended on k, the normalization of the density, but the answer to the partial differential equation does not depend on k. In fact, it would be killed by that formula. I'm taking the gradient of the log. In the first example, the Gaussian case, same thing. The partial differential equation depends on k, but the answer to the partial differential equation does not depend on k. Now, why do I bother putting that fact in red and showing you 3 examples where this happens? Well, it turns out this is one of the keys to making this theory work. If you had a theory where that did not happen, the theory wouldn't be any good. All practical algorithms that are robust in high dimensions that we know of have this property of being invariant with respect to the normalization. Normalizing a probability density, an arbitrary probability density in high dimensional space is well known by statisticians to be a very difficult problem. So our approach to this problem is don't even attempt to solve the problem, but rather avoid it. Go around it. So far, and you might ask the question, which of these 25 different methods result in algorithms, laws of motion, which are invariant with respect to k? Those are the ones that work. We discovered this the hard way. We discovered it by numerical experiments. We tried essentially all of those 25 different methods. And we found, and we were confused for years. We were confused for about 5 years. We had some methods that worked and other methods that barely worked, had to do very special, strange things to get them to work, and other methods that didn't work at all. So what separates these two classes of good algorithms versus bad algorithms? It's the invariance to k. It turns out that other people understand this. I heard a lecture in 2011 by Emily Walsh, who had just completed her doctorate at Bath University, where she was solving a transport problem, which is essentially what I'm doing. And she was solving two Poisson's equations to compute the law of motion, to flow the particles. And she was explaining that her algorithm required the normalization of the conditional probability density, and that she was required to compute that normalization to machine precision, that is 64-bit floating point accuracy. And when I heard that, I was in the room, I was listening to her very nice talk. When I heard that, a chill went up and down my spine. In fact, just now, believe it or not, a chill went up and down my spine. It was such a confirmation of this basic, to me now, crucial fact that if you want good algorithms that work robustly in this class of transport problems, they had better be invariant with respect to the normalization. Interestingly, not everybody seems to know that. So, Gromov. What we do here is we try and intimidate the audience by a massive display of partial differential equations. Isn't that the first step in this process? No, sorry. Here we're adding a level of complexity, which is the randomness to the flow. The first three flows that I showed you, the Gaussian, the incompressible, and the geodesic flow, were all deterministic flows. No randomness at all in the law of motion. Here we're adding a randomness on purpose, just for fun, and let's see what happens. Turns out it's quite a good idea to do this, by the way. So when you do that, you have to solve the Fokker-Planck equation. You have to plug in the high school definition of what we want. Log p is equal, by definition, log g plus lambda log h minus log k. Plug it in, and then we know, as a result of the little story that I just told you, we don't like k. In fact, we don't like it so much that now we're strongly motivated to kill it in the partial differential equation. How would you do that? Just differentiate with respect to x. K is not a function of x. Kills it. Great. So k was there, and then we killed it. So you get that partial differential equation. And as you can see, we have the unknown f, which is the drift term, d-dimensional drift term. But we also have another unknown, which is this q. Q is a matrix. It's a d by d matrix. It's a covariance matrix of the Brownian motion. It's a symmetric, positive semi-definite matrix. Lots of variables in Q, the matrix Q, on the order of d squared variables. D times d plus 1 over 2, actually, for symmetric matrix, ignoring the constraint that it's positive semi-definite. So a quadratic on the order d squared unknowns in that matrix Q, and d unknowns in F. But how many equations have I got? I've got d equations. So this is a highly underdetermined partial differential equation for dimension greater than 1. In one dimension, it is, in fact, determined in a sense. So how do you solve that? Well, it's sort of a mess, isn't it? It's this bottom partial differential equation. You stare at it, and I mean, even though you've only been looking at it for a few minutes, I looked at it for about 3 years, and nothing came to mind. But one day, something did come to mind, which is the following. You say, look at this. Look at this. The first two terms, that d by dx log h and the Hessian of log p, those two terms, suppose those are equal. Just suppose those are equal. How could we make that come true? We could make that come true by making these last three terms all sum to 0. The individual terms are not 0, but they sum to 0. How could we make that happen? We could make that happen by choice of Q, the matrix Q. We have plenty of unknowns, plenty of free variables in the matrix Q. I have d equations. It's an algebraic equation, by the way. Well, yeah. Well, Q might be a function of x, so it's not an algebraic equation. Anyway, so that works. And I'll show you what that does. So the law of motion is displayed here. F, the drift, is exactly the same as the geodesic flow. That's how I knew that was a good idea. And then Q, it turns out, if the process is Gaussian, can be computed explicitly in terms of things that you know. It's, again, one line of MATLAB. But of course, the problems that we are really interested in are not Gaussian problems, not Gaussian linear problems. We're interested in much more general problems. So it turns out, last year, we realized that the general solution, in a sense, is that bottom for Q is that bottom equation. So now we have a general solution for this highly underdetermined linear partial differential equation. And it works. And the one below it works much better than the one above it for lots of applications that are highly non-Gaussian. It works as long as, of course, the expression makes sense. You need I'm, of course, assuming that the densities are nowhere vanishing. That allows me to take logarithms and keep the logarithm as a real variable. So nowhere vanishing densities, smooth densities, so I can compute the Hessians and the gradients. So I assume twice continuously differentiable densities. And I am not assuming that the conditional density is log concave, which is a favorite hypothesis to prove certain theorems in this field. But I do have to assume that the likelihood is log concave. Not strictly log concave, but log concave. Otherwise, it's perfectly general. So nowhere vanishing, twice continuously differentiable, and the likelihood has to be log concave. That's pretty general. That makes us very happy. We can apply this for lots of problems. So this is actually an application of Gromov's theorem, Gromov's little theorem on page 149 of the book that he published in 1986 in English, Springer Verlag. Again, this is a highly underdetermined partial differential equation. That's the hallmark of Gromov's work. The hallmark of Gromov's work, we want the image to appear. Where's Gromov? Oh, I see what's happening. This took a long time. So anyway, there's a paper that you can get, and it works awfully well. Even for 100-dimensional problems, you get the good convergence of accuracy versus number of particles, no trouble. It doesn't look like there's any cursor dimensionality, at least for this class of problems, up to dimension 100. That doesn't mean that that things are not going to go wild after that. I have absolutely no theoretical proof that I'm beating the cursor dimensionality in general. All I have is proof by MATLAB for a specific set of examples, which I've picked. They're my examples. I haven't come in with some independent test team that tries to torture the theory and show that something is better. So here's Gromov. Okay. So here's a photograph of Gromov about 20 years ago. He looks, actually I saw him 3 years ago in Paris, and he looks pretty good. Anyway, even today, even 3 years ago. So he's looking very impish. He looks like he knows something. It looks like he knows a lot that you don't know. Well, that expression is really due to the fact that he is a trickster. He is willing to take the boring, the wonderful classic field of partial differential equations and twist it in a way that is really fun. Even just thinking about underdetermined partial differential equations is different. If you run into a real mathematician who does partial differential equations, the usual attitude about underdetermined partial differential equations, especially linear underdetermined partial differential equations, is that they're beneath contempt. Meaning, you will not get a doctorate from any place by writing up a thesis and doing research in underdetermined linear partial differential equations. They're too easy. So I can show you the books that say that. Nevertheless, Gromov was interested in nonlinear partial differential equations, and this part was a stepping stone to that. Gromov has the following result on page 149 of his book. Gromov says, if I have a sufficiently underdetermined linear constant coefficient partial differential equation, I can solve it without any integration. Just apply a linear differential operator to the right-hand side of that partial differential equation. And you know the practical implication of that. It's that we can do it very fast and accurately. I mean, differentiation, absolutely no problem compared to solving, inverting a linear differential operator. So when does this happen? It's only if the functions involved are sufficiently smooth, and Gromov assumes C infinity, because he's very lazy. Well, I'm sorry, he's not lazy. He wants to stay out of trouble. So he assumes C infinity functions. He also computes that the number of equations, the number of unknowns has to be at least the number of equations, linearly independent equations, plus the dimension of x. Very simple. The number of unknowns must be at least the number of linearly independent equations, plus the dimension of x. That's Gromov's theorem. It's not a deep theorem. It's actually pretty easy to prove it in about half a page. He proves it in about half a page. But for a talk in the middle of the afternoon like this, I think a better entree to understand what's going on is to see the simplest non-trivial example. Russian mathematicians are famous for desiring the simplest non-trivial example. Of course, Gromov never put anything like this in any of his books or papers. His book is famously difficult to read and understand. So here's the simplest non-trivial example that we cooked up. It's a single linear partial differential equation. 3 unknown functions, q1, q2, q3. The dimensionality of the state vector is 2, x1 and x2. So this indeed satisfies the hypothesis of Gromov's theorem. It's a linear constant coefficient partial differential equation, and the number of unknowns, which is 3, is in fact at least equal to the number of equations, which is 1, plus the dimension of x, which is 2. So the hypothesis of Gromov's theorem is in fact satisfied. And the solution is evident. M is some linear differential operator according to Gromov. Gromov's theorem says there exists an M. There exists a linear differential operator, call it M, which when you operate on the right-hand side, which has to be smooth, sufficiently smooth, then you get the answer. And just a little poking around, you can see that that is the exact solution. and just plug it back into the original equation. You get minus the Hessian of eta plus the Hessian of eta is equal to eta plus eta. So these two Hessians cancel. These two second derivatives cancel as long as eta is at least a twice continuously differentiable function. Really nice and simple, easy to understand example. Okay, you can easily generalize it to higher dimensions, no trouble there. It highlights the fact that this would not work unless eta was sufficiently smooth. Wouldn't work. If you asked Mathematica, or your favorite symbol manipulation software, to find a solution of that linear constant coefficient partial differential equation, good luck. It won't do it. You would have to tell Mathematica that it's a sufficiently smooth function. So I'm picturing the Kähler-Cartan calculus, exterior calculus, which has embedded in it as a rule that d squared is equal to 0. And those of you who know what exterior differential forms are knows that d squared equals 0 is equivalent to the equality of the second mixed partials. That's the right calculus to attempt to make progress in this area. And I'm hoping, actually, the next time I come back to Stony Brook to find that you've pursued that line of research with profit and you've generated all sorts of other solutions. But in the meantime, we did it by sticks and stones. So we can generalize Gromov's result to less smoothness, more general functions, and we can display them, and et cetera, et cetera. So waiting for this computer. I'm waiting for this laptop. Oh, so why would you make something stochastic if you didn't have to? Why would you make something stochastic as a matter of choice? I mean, why? Well, this is quite an important question for us. It's almost as important. It's okay. Nah, don't worry. So the first obvious answer is, well, you get better performance. You get better more accurate filter performance if you make it stochastic. There's a second answer. Actually, the fourth one in red that I like. You could not use Gromov's theorem unless you had enough unknowns. And you can get enough unknowns if you add the Q matrix as an unknown to the partial differential equation, which corresponds to making the flow stochastic. And then exploit the fact that you can solve this, in a sense, more complicated partial differential equation exactly with very low computational complexity as a result of Gromov's theorem. So we're doing two things. We're getting better performance, but the way that we did it was to exploit Gromov's theorem. And Gromov's theorem wouldn't work at all. The hypothesis of Gromov's theorem wouldn't be correct in this case unless I had enough unknowns. So this is really weird. This is really different. Many of you in this room probably go around trying to reduce dimensionality with compressed sensing or something else. Any normal person, any normal engineer, physicist, chemist, applied mathematician would think, oh, reducing the number of unknowns is the right approach. No. Gromov doesn't agree with you. And I don't agree with you in this particular case. And if you think about it, if you think about other algorithms, the whole rafter of different algorithms, what are the algorithms that are famous, well-known, robust, are actually used? They're all random. Hastings Metropolis is random. Hamiltonian Monte Carlo flow is random. Langevin, of course, is random. Ensemble Kalman filter did not start out as random, but within a few years, engineers rapidly discovered that we'd better add some artificial measurement noise, and that makes it work much better. And then the theory followed from that to explain why that was a good idea. Our early particle flow filters were not random. They solved a lot of problems very nicely, but they didn't solve the problems as rapidly, as accurately, as nicely as the latest theory. And then, so I would submit, well, there is one outlier on the chart, and that's optimal transport. Optimal transport is practiced by lots of great mathematicians like Soudrik-Villani and Brognier. They tend to be largely French mathematicians or Berkeley mathematicians or Canadian mathematicians. Mathematical optimal transport, by and large, is almost exclusively asks for laws of motion that are deterministic, not random. And I would think that doing optimal transport for random problems would be even more fun than deterministic problems.
It's been done.
By who?
Well, by us, for example.
Oh, great.
No, but we're not the only one who that happens. So instead of having the continuity equation, you add a diffusion term. That's a Fokker-Planck equation.
Yep.
And you can also take noise into consideration in the kinetic energy that you're minimizing over that. So in other words, noise is taken into account in the formula. And actually, you're completely right. For real problems, you have to put in the noise. I mean, because real problems have noise.
So I need to read that paper or set of papers. Please, Alan.
I'll send you, of course.
Thank you. So this trip was worthwhile for many reasons. That's what, as usual. I know I could count on Alan for something like that. So sort of a grand summary. There's a paper that's free online. You don't have to have a magical password. You don't have to be a member of the Royal Society or even the Ig Nobel Society. Thank you very much for your attention. Any more questions? Did I do any justice to helping you see what I was talking about with particle flow?
If I can ask the question, I try to envision how I would implement it, and so I'm not sure that I'm clear in all the steps that I need to do it. So when you start with the normal particle filter, I guess you start with the having the observations, the likelihood function, and also the motion model or some the transition model from one step to the next.
Yep.
And then the update is that by multiplication, like you showed.
Exactly.
Now we did the flow. I think, can you walk me through what else do I need?
The particle flow simply replaces Bayes' rule with the flow. You never do a multiplication to implement Bayes' rule in our algorithm, but rather you take out the multiplication for Bayes' rule and replace it with the flow of particles. That's all. That's the only difference. So take any particle filter, change that one line, take out the one line that does the multiply and replace it with the 2 or 3 or 4 lines that does the particle flow.
Can you show me that equation again?
Yes. For example, you could use that law of motion. X is the numerical value of the state at each particle.
Right.
So compute the matrix A, compute the vector B, and this is 3 lines of MATLAB.
And then what do you do?
And then numerically integrate that law of motion, going from the initial condition, which is lambda equals 0, in little steps, 10 equal Euler steps. And by the time you get to unity, lambda equal unity, you have moved the particles to the correct posteriori Probie density. Just like the movie. You do that. You make this movie. There's the initial condition. That's the initial set of random particles. And then you do 10 Euler steps, and I'm showing every single Euler step. That's all. It's too simple. It's not complicated.